Delay estimation topic, we have RC delay model, Lmos delay model, as well as linear delay model. Three types of delay modeling we have to see. The first topic is RC delay modeling. So before getting into the RC delay modeling, uh, we need to know the equation which is used to calculate RC delay. From the name itself, we need to calculate the equivalent resistance as well as equivalent capacitance to the circuit or the design what we are getting to calculate delay. Then we have to apply in the equation tau equal to RC. So this is the main basic equation to calculate RC delay model. Tau equal to RC. Tau is the delay constant or time constant. So this picture represents the equivalent circuit of both Nmos and PMOS with respect to internal resistance as well as capacitance associated with both the transistors. So if you know this equivalent circuit only, we can proceed with circuit. For example, if you want to calculate RC delay of an inverter, so we will be connecting PMOS as well as NMOS equivalent circuit together. So this is the connection of two inverters. Here we will be considering the output equivalent circuit of the first stage and the input equivalent circuit of the second stage. Actually, in the while calculating a delay, we can able to calculate the delay of the circuit with respect to uh, the load, or it has to drive another circuit. Then only we can able to calculate. So that's why they have cascaded two inverters of the same kind so that we can able to calculate the delay of a particular inverter. So here the first stage depict the output capacitance and the second stage depict the input capacitance. So actually this circuit is obtained by combining these two. Here in the first stage we are not considering the input capacitance. Only we are counting only the output capacitance. In the second stage, we are going to consider only the input capacitance. So here, while seeing the circuit, here when circuit is on, we will not be considering this non-switching capacitance. This 2C will be eliminated. So all these capacitors are connected in parallel, so we can add it in order to calculate the equivalent capacitance. So you will get 6C here. So this will be the equivalent circuit related to one inverter. So while calculating delay modeling, we have to multiply R into 6. So 6RC will be the equivalent delay constant of or RC delay of an inverter. So we have to keep in mind that while calculating the delay of a particular circuit, we have to calculate the equivalent resistance as well as equivalent capacitance. So actually, how they are arriving into this equivalent network is, so as we have discussed in the first class, so the size of the PMOS has to be chosen twice than NMOS because the majority charge carriers are electrons for NMOS. So considerably, it will be more faster than your PMOS. So in order to match the conductivity, we need to have sufficient charge carriers for PMOSs. So that's why we have to choose the size of the PMOS is twice. So obviously, if the size is high, the resistance also will be high. So we have to choose the resistance value of PMOS should be twice than NMOS. The rest of the cases all are same. So why the capacitors are connected to ground is, so while operating an NMOS, so we need to get the strong zero at the output. At that time, all the capacitor has to be discharged in order to get the zero voltage at the output. That's why the capacitors are connected to ground in case of NMOS. So while dealing with the PMOS, we have to get strong one at the output. So at that time, capacitor has to be charged at to VDD. So that's why all the capacitors are connected to VDD in case of PMOS. So this is the equivalent circuit of NMOS and PMOS. So with respect to an NMOS, PMOS equivalent circuit, so whatever may be the logic they are giving, you can able to calculate the RC delay model. So you have to connect properly the equivalent uh, circuits of NMOS and PMOS. Initially, you can able to find out the equivalent resistance. Here, one condition that both the NMOS and PMOS has to drive the same output current. Then only it can able to calculate. You can able to calculate the resistance value. So, in order to calculate resistance value, you can keep in mind that all the connections, all the PMOS and NMOS have to deliver the same output current. And then I will tell how to calculate this K value. Actually, for a non-skew, we have seen unskew, high skew and low skew. In an unskew network, you will be having the K value of NMOS as 1 and the PMOS is twice 1. So K value of PMOS will be 2 and the NMOS will be 1 in the case of an inverter. That's why they have connected 2, 1 like this. So K value of PMOS is 2 and N value is NMOS K value is 1. So it is a fixed thing in the case of unskewed network. So based on this only we can able to calculate the K value for the rest of the networks. So here they have connected, they have shown 3 input AND gate. So in order to calculate the K value, so we know the base K value for NMOS and PMOS already. So now we have to count the number of stages. So if transistors are connected in parallel, we have to count it as a single stage. If the transistors are connected in series, we can able to add the number of stages. So as per this connection, at the NMOS side we have 3 stages and PMOS side we have only 1 stage. So while by considering this, so in order to calculate each and every K value of the transistor, we have to multiply the base K value of that particular transistor with the number of stages. So as you already know, the base K value of NMOS is 1. So here you have number of stages 3. So 3 into 1, 3. So that's why the K value of each and every NMOS is 3. So while considering PMOS, so you have only single stage base K value of your PMOS is 2. You have 1 stage, so 2 into 1. So 2 will be the K value of so each and every network. You see this NOR3 structure, you have 3 NMOSs connected in parallel and 3 PMOSs connected in series. So while considering NMOS, you have only single stage because all the NMOSs are connected in parallel. So you have only single stage. The base K value of the NMOS is 1. So it has to be multiplied with the number of stages, that is 1. So 1 into 1. So all the NMOSs will be getting the K value as 1, 1, 1, 1. And here you see you have 3 PMOSs connected in series. So you have 3 stages of PMOSs. The base K value of PMOS is 2. So 2 into number of stages. So 3 stages are there. 2 into 3, 6. So each PMOS will get in the K value as 6. So based on the K value only, we can able to calculate the input capacitance. So in order to calculate the input capacitance, if you see the equivalent circuit of NMOS and PMOS. Yeah. So if you see the equivalent circuit of NMOS and PMOS, so we are going to calculate only the input capacitance. Okay. Because this input capacitance are coming as the from the second stage of the inverter. So every time we will be calculating if you are specifying input capacitance. Actually, these capacitance effects are not there actually. Whenever we specify the input capacitance, it is appearing as the uh, input capacitance of the load from the second stage. That is coming from the second stage. First stage, we are not having any input capacitance always because we are not driving any, we are not, first stage is not driven by any of the other previous stages. So whenever we specify an input capacitance, we will be calculating with respect to the second stage of it. Actually, we are seeing this capacitance effect and all, right? Actually, these capacitance effects are not physically present. These are not the physically present capacitance. We have seen CV characteristics, right? So for every transistor, you will be having some diffusion capacitance, intrinsic capacitance, overlapping capacitance you might have seen already. All these capacitance effects only acting as input as well as output capacitance. Physically, you don't have any capacitance effect in your transistor. So these internal and external capacitance effects are coming from the CV characteristics what we have seen already. So while calculating the input capacitance of Nmos, we have to consider K into C. For PMOS also the equation is K into C. Now we have seen how to calculate this K value. So then it is easy to calculate the input capacitance. Why I am specifying the input capacitance here is in linear delay model, we will be seeing logical effort calculation at all. At that time, you need to know how to calculate the input capacitance. Generally, you can able to calculate the logical effort. So while calculating equivalent capacitance, you have to add input capacitance as well as output capacitance as we have specified here. Now I am mentioning only about input capacitance. So for the same circuit, if you want to calculate the input capacitance of this NOR3, so you need to consider any one of the input. So for example, if you are considering A input, so here the K value is 6, here the K value is 1. So total input capacitance of the network will be 7. So we need to calculate the input capacitance based on any one of the inputs. So if you see here in this example of NAND 3, so you will be calculating the input capacitance based on any one of the input. So if you consider this first input, so you will be having the K value here 3, here 2. So you will be having the input capacitance of the entire network only will be 5C. 5C will be the input capacitance of this NAND. So for consider while considering NOR 3, you will be having 6 plus 1, 7. So we will be considering only single input for calculating the input capacity. So that you should not forget. Otherwise, you will be in confusion. So the equivalent from the equivalent circuit at the time of rising as well as falling. Actually, the rising network is coming with respect to the equivalent circuit related to CMOS side. So this is the equivalent circuit related to NMOS side. So in order to calculate the resistance value, I have already mentioned the rising time current as well as falling time current has to be equal. Then only you can able to calculate the equivalent resistance. So that's all about your RC delay modeling. The second type is your Lmos delay model. In the Lmos delay model, we will be considering as the entire network as a ladder-like structure. So your equation will be modifying as the equivalent resistance of the all the network into equivalent resistance of all the capacitance present in the network. So it will become summation of RC. So if you have a ladder-like structure here, so you can able to represent all the networks as the ladder-like structure that we have already mentioned, right? For calculating that inverter, we have mentioned as R into 6C like structure. So here you will be considering all the capacitance effect present in the circuit. So you can able to represent your particular network in terms of a ladder-like structure. So here you will be adding all the capacitance and adding all the resistance. So finally you will be multiplying. So the summation RC will be the equation of Lmos delay model. So many times you might have seen your university previous question papers. Many times they have asked you to represent the write the Lmos delay model equation in 2 marks. But while coming to linear delay model, it is very important topic under delay modeling. So in linear delay model, you will be having small 2 marks as well as you may get some big part C problems also from linear delay model. Actually, in linear delay model, what we are doing, we are going to plot the graph between normalized delay as well as electrical effort. So I will specify to calculate how to calculate delay as well as electrical effort, logical effort. So you can able to see this graph. So here we will be plotting the normalized delay versus electrical effort means how many output circuit can be driven by a logic, a particular gate. We are going to calculate the delay of a particular gate. So the electrical effort refers how many other circuits it can able to drive. That is called as fan out. So we are plotting the graph between these two parameters. All the lines will be as a linear increasing or decreasing. So that's why the delay modeling name itself linear delay model. So for that we have to initially calculate two different parameters. One is logical effort and second one is parasitic delay. Here the delay represent F is the effort delay plus parasitic delay. For calculating effort delay, we need to calculate logical effort as well as electrical effort. Actually, F is the effort delay plus parasitic delay. F can be calculated with respect to G is logical effort, H is the electrical effort. So first we can see how to calculate logical effort. So while calculating logical effort, you have to be keep in mind that logical effort of a network can be calculated as uh, the ratio of input capacitance to that particular gate which is under test divided by the logical effort of an unit inverter. So keep in mind that both has to deliver the same output current. Actually, the gate which we are going to calculate logical effort, that gate as well as the unit inverter will be having the should have the same output current. Then only we can able to compare those two networks. Here they have seen and shared an example of how to calculate uh, logical effort for an unit inverter as well as an AND 3. Already we have seen how to calculate this K value, right? So from this K value, we can able to see that the input capacitance of this inverter is 3. So in order to calculate the logic effort of this inverter itself, so we will be calculating 3 divided by 3. That is 1 is the logical effort of the unit inverter. So according to the definition of logic effort, so in order to calculate the logical effort, we need to take the ratio of the input capacitance of the gate. Here the gate is inverter itself. So this input capacitance 3. So divided by the input capacitance of the unit inverter. It is already calculated as 3. So 3 by 3 is 1 is the logical effort of this particular gate. So if you want to calculate the logical effort of this NAND gate, already we have calculated the K value. So input capacitance have to be calculated with respect to either of one input. Here we have three inputs. We need to take any one input. For example, if we are taking A, so the A is from this particular A is applied to particular this CMOS and NMOS. Here it is 2C, here it is 3C. So input capacitance will be 5C. So that is only they have mentioned. So divided by the input capacitance of the unit inverter. So 5 by 3. So likewise for CMOS NOR gate, so 1 plus 6, 7. So 7 by 3. So while seeing this logic, so 5 by 3, so if you go for another 4 input NAND gate, so here it will become 4, 4, 4. Here it will become 2 only. There won't be any change. Because if you are connecting again one CMOS in parallel, the K value will be remain same, 2 only. Since we have only single stage. So if you are connecting another NMOS in series, so this K value will become 4. So then 4 plus 2, 6 will be the input capacitance. So 6 by 3 will be the logical effort. Then if you are increasing the input of the NAND again, so if you are considering 5 input NAND gate, the all K value of NMOS will become 5. Here it will become 2 only. So 7 by 3. So for 3 input, it is 5 by 3. 4 input, it is 6 by 3. 7 input, it is, sorry, 5 input, it is 7 by 3. So depending on the number of input, plus 2 value is coming in the numerator. So we can able to conclude that the general expression to calculate NAND gate is n plus 2 divided by 3, where n is the number of inputs. In the case of PMOS, in the case of NOR gate, so as the input increases, there is no change in the NMOS side, but it will become doubled again. So here 7 by 3 for 3 input. So if you are going for 4 input, it will become 8 by 3. So 4 into 2, like that, 8 by 3. Then if you are going for 5 input, it will become 10 by 3. So 8 plus 1, 9 by 3, 10 plus 1, 11 by 3. If you are going for again 6 input, it will become 12 plus 1, 13 by 3. So if you compare all these things, so 7 by 3, 9 by 3, 11 by 3, for 3 input it is 7. So 2n plus 1 is the formula for numerator. So if you are going for 4 input, so 8 plus 1, 9. So 2 into 4 plus 1. That is the equation. For 5 input, it is 10 plus 1, 11, right? So 2 into 5 plus 1. The numerator general expression is 2n plus 1. So divided by 3 is the logical effort. General expression to calculate for NOR. That only they have compared in this table. For inverter, you will be having only one input. So 3 by 3, the formula is 1. For NAND gate, 4 by 3, 5 by 3, 6 by 3. So as we have specified, the general expression is n plus 2 divided by 2. These type of expression they have asked in several 2 marks. So if you know the general expression, you can able to come with this values very easily. For multiplexers, irrespective of the input, the value is 2. If we go for XOR gates, the value is 4, 6, 8, or 16, like that it will go. For XNOR, it is 4, 12, 16, 8, like that it will go. So depending on the number of bits in variation. So if you see parasitic, this is a concept about logical effort. Do you have any doubt in calculating logical effort as of now? This is a very, very important topic. Any doubts? Shall we move on to chat? Sir, how do we ensure same current is delivered? So same current is delivered is calculated based on the resistance value. So we will be, in order to get the same output current, so we need to have same resistance, right? So you have seen the general expression. After calculating that only, we are coming to that K value simplification. So if you see this equivalent circuit. Here you will be having R by K, here you will be having 2R by K. Okay. So in order to get the same output current, you have to equate those two resistance value in the case of CMOS and Lmos, and we have to calculate. For example, R by K. For example, R is the resistance you need to get, capital R. So in order to calculate the K value, you have to equate R with respect to R by K. So R equal to R by K. So K value will become 1. That's why we are choosing the K value as 1. So here also, 2R by K will be equated to R. So in order to get R, we have to substitute 2 instead of K. So if you have the same resistance, then we will be having the same output current. That is the logic. For every calculation, based on this only, we are setting the K value. Okay. So the shortcut what we have seen how to calculate the K, it will always satisfy the equal amount of current flow. So no need to mind about that. Actually, this is the concept behind how to set the K value. So whatever may be the equivalent resistance you are getting, that equivalent resistance has to be equated with the normal R to find the K. Here also, in the case of CMOS also. So if you follow that shortcut, it will automatically, we will get the K value, which is for same output current. Are you all clear, or any elaboration is required? Satvika, are you clear? Okay. Your session may end up within 2 or 3 minutes. Again, you can restart. Okay. As we have started around 11 o'clock. So by 11:35 or 11:40, the session will be end automatically. You can log in. So we have seen logical effort. Then we have to go for parasitic delay. So parasitic delay, while calculating that, we have to keep in mind that uh, it is also the case like your logical effort. But so as per the definition, the parasitic delay of a gate is the delay of the gate when it drives zero load. So we are while considering RC delay model, we have connected particular gate for the delay to be calculated. We have connected to the same load, right? Here we should not connect any load, so we have to calculate the parasitic delay. So these are all the general expression for calculating parasitic delay. So whenever there is no load, you don't have any extra capacitance effect. So you have to take care only the particular input capacitance to calculate the load. So for inverter, it is parasitic delay is 1. For the AND gate, it is the general expression is n. For the OR gate, also general expression is n. So as per the number of input, that many parasitic delay value will be there. For multiplexers and tri-state buffers, it will be 2n, depending on the number of inputs. The multi-stage logic network. So they will be giving the connectivity of different logics, and they may ask you to calculate the electrical effort, the path effort, as well as parasitic delay. So you can able to go through this particular example. They have clearly given how to calculate the electrical effort, path effort, and logical effort. So while coming to the next session, we go through, and if you have any doubt, you can clear, because the same diagram they have asked for 15 marks as a part C in two different question papers. In one question paper, they have given the same diagram. In another question paper, they have slightly modified the values inside, and they have given the same diagram in order to calculate the path effort and the logical. So you can go through the examples.